Hi everyone, welcome to topic 6.2, hypothesis testing for independent sample tests. First, let's distinguish between tests. As discussed in topic 6.1, for a one sample test we're comparing our sample mean to our hypothesized population parameter, which I often like to think of as a benchmark value. For example, is the average weight of a bag of potato chips equal to 80 grams as specified on the packaging? As you can see with these examples, it only involves the collection of one sample of data and the sample mean is then compared to the benchmark value. This is different to two sample and match paired tests. In this topic we are looking at independent samples where we are comparing the mean of two groups. These groups must be independent in the sense that an individual belongs to one or other group. Research questions for these tests are more along the lines of, is there a gender pay gap within our organisation? Here we are comparing the average wages for males and females. Similarly, we might compare the average sales for Team A compared to Team B. For independent samples, as discussed, the two groups need to be separate. mu1 represents the mean for population 1 and mu2 is the mean for population 2. Similar to the one sample test, there are times when we will calculate a Z statistic and refer to the Z distribution, and other times when the T distribution is more relevant. To decide on this, again, it is whether the population variance is known. If the population variances are known for both groups, we use the Z distribution. If the population variances are unknown but assumed equal, we use the T distribution and the formula for pooled variance. Now, if the population variances are unknown and not assumed equal, we still use the T distribution, but instead of pooling the variances, we use a different formula with the sample variances. Let's work through some examples. First, let's discuss the hypotheses. When we are looking at independent samples, there are three different sets of hypotheses. When testing for a difference, we use the two-tailed test, so we can write HO and HA as shown on the slide. We can write it as mu1 subtract mu2 equals 0, and mu1 subtract mu2 does not equal 0. Alternatively, and my preferred way, is to simply write HO colon mu1 equals mu2, and HA colon mu1 does not equal mu2. Either way, we need to specify what 1 and 2 are. 1 maybe refers to females, 2 to males, 1 to Team A, 2 to Team B, for example. Okay, so that's for the two-tailed test when we're testing a difference. Now for the directional tests. The hypotheses for the one-tail lower tail test are shown in the middle box. Here, HO is mu1 greater than or equal to mu2, and for HA, the alternative hypothesis, mu1 is less than mu2. The hypotheses for the one-tail upper tail test are shown in the last box on the right of the slide. So here, where the population variances are known, we use the Z distribution, and the formulas on the slide. If the population variances are unknown, which is mostly the case, but the population variances are assumed equal, we pool the variances and use the formula on the slide. Although this formula looks complicated, it is more tedious than complicated. Have a closer look. You know all these symbols, but running the numbers through a calculator takes many steps and some time. Thankfully, Excel computes these values in seconds. Note the degrees of freedom are now calculated and with sample sizes added together, and we subtract 2. Now, if the population variances are unknown and cannot be assumed equal, we use the formula on the slide. Note the sample variances are used separately throughout the formulas. Again, Excel can compute these figures with a few clicks. Phew, I hear you say. Okay, first example. A consumer advocate analyses the sugar content in 2 brands of cough medicine. A sample of 20 bottles of brand A are randomly selected, and a sample of 25 bottles of brand B are also selected. The sample means and sample standard deviations are presented on the slide. As the population variances are unknown, we will be using the T distribution, and the sample standard deviations being very close in value means that we will use assumed equality for variances and the pooled variance approach. Now it's your turn. Press pause on the video and write down the null and alternative hypotheses for this example. I'll provide the solution next. Okay. So as this is a test of the difference between the means, it is a two-tailed test. If you wrote HO colon mu1 equals mu2 or mu1 subtract mu2 equals 0, you are correct. The alternative hypothesis contains the not equals to sign. On this slide you can see all of those tedious calculations. I always think it's a good way to learn this by looking at the formulas and seeing where the numbers come from when we're calculating our T and Z, but I'm also relieved that Excel will do this for us. Now here you can see the pooled variances included to calculate a t-statistic of negative 3.89. The t-critical was determined by looking up the tables, the t-tables, using the degrees of freedom and alpha. The t-critical value is 2.017. Have a look in your t-table on page 732. Look down the page for degrees of freedom, which is 20 plus 25 subtract 2, so there are 43 degrees of freedom. Then look across to an alpha of 0.025, as this is a two-tailed test. The t-critical value is 2.07, positive and negative. Okay, now let's make a decision and draw a conclusion. Since the t-statistic of negative 3.89 is less than the negative t-critical value of negative 2.017, we reject the null hypothesis. The conclusion then is that there is enough evidence that the two brands differ in relation to average sugar levels. Now here we have an example where the population standard deviations are known, and so we will be calculating a Z statistic and referring to the Z distribution. In particular, the researcher wants to determine whether the average food expenditure for households in City 1 is greater than the average food spend for households in City 2. A survey is conducted and 35 households are randomly selected from City 1 and 30 randomly selected from City 2. The sample data is shown on the slide together with the population standard deviations. So see, the sample mean for City 1 is $164 and for City 2 it's $159. So the hypotheses relate to whether $164 is significantly greater than $159. Look, we know that 164 is a higher number than 159, but the question is about statistical significance, because we also know that there are differences from sample to sample, and therefore there is always noise in the data. So is this difference a real difference or due to chance? I know you are dying to find the answer, but before we do so, please stop the video and write down the null and alternative hypothesis. Okay, so the alternative hypothesis always relates to the research question, and here it is, HA colon mu1 greater than mu2. The null hypothesis then is the exact opposite and written as HO colon mu1 less than or equal to mu2. You can see this written on the next slide. So here are the hypotheses which I know you got correct because you are all hypotheses experts by now. Okay, so now here's the formula for calculating Z. It's not too complicated, is it? The Z statistic is calculated as 1.85. Now on to making a decision and drawing a conclusion. Let's use the p-value approach since we have calculated a Z statistic. We can look up our Z tables, and 1.85 relates to a p-value of 0.9678. 1 subtract this number leaves us with 0.0322. As this is less than our alpha level set at 0.05, we reject the null hypothesis. We can then conclude that there is enough evidence that the average weekly food spend for households in City 1 is greater than the average weekly food spend for households in City 2. Now I want to show you some Excel output, as this unit is more focused on interpretation and decisions than tedious calculations. Here is an example of 10 firms in the gold industry and 10 in the oil industry. We may be interested in whether the average returns differ. The hypotheses are presented on the slide together with the data. We will assume the distributions are normal and the variance is unknown and unequal. Here is the Excel output. Now you have to be a little careful reading the output. First you can see the means for both gold and oil, 16 and 17.3 respectively. Next the variances are presented and the sample size. The hypothesized mean difference is 0 because we're not expecting a difference and we're hypothesizing for that. Our degrees of freedom of 17 is calculated from that very awful and tedious calculation a few slides ago. And then our t-statistic is presented as negative 0.3023. The next two lines of output relate to a one-tailed test, and following that, the last two lines of output relate to a two-tailed test. This is what we are interested in for this example. Excel provides both sets of output to account for different hypotheses. Okay, so the p-value for a two-tailed test is 0.7661. This is greater than 0.05 and therefore we do not reject HO. Similarly, if we look at the t statistic in relation to the t critical value, the t statistic of negative 0.3023 is certainly between negative 2.1098 and 2.1098. The conclusion is therefore something like there is not enough evidence to conclude that the two industries differ in terms of average returns. Well done, everyone.